transforming exponential functions. This goes with 15.5 in your text. Your EQ, how does the graph of f of x equals a times b to the x power change when a and b are changed? All right, so learning goal, I can graph an exponential function. And so this is just some review from this week, okay? This right here, this y equals a times b to the x power. This is the general form of an exponential function. It'll look like this, all right? And then some different things will happen depending on the values of a and b. So right here, if a is greater than 0 and b is greater than 1, you're going to have this type of a graph show up. And I encourage you guys, use Desmos, the graphing calculator, as you work through these different problems to check your work and make sure you're doing things correctly. If a happens to be less than 0, so a is now a negative, but b is still greater than 1, then our graph becomes reflected over the x-axis, all right? And so now it's like a mirror image over the x-axis of what we had before. When a is greater than 0, but now b is a fraction contained where it's less than 1 but greater than 0, so a proper fraction here. What happens is, if I come back and compare it to the original one here, well, it's a reflection again, but this time it's being reflected across the y-axis. Okay, it's like a mirror image where the y-axis is your mirror. And then this last possibility here, this is when a is less than 0 and b is also a fraction, proper fraction, less than 1 and greater than 0. And they're giving you an example in pink of each of these, what that might look like. So it's two reflections basically. So you reflect it over the x-axis and over the y-axis, and it doesn't matter which one you think about doing first, it gives you this image here. So based on these 4 different ways your graph can go, it's based on what would happen with the values of a, or, and b. Okay, so when we talk about stretching and compressing graphs, okay, we can do that. And so this is some vocabulary. If I talk about a vertical stretch, it's a type of transformation that pulls the graph away from the x-axis, all right? By multiplying the y value of each xy pair by a, where the absolute value of a is greater than 1, the graph is stretched by a factor of the absolute value of a. And over here, this picture, there's 2 curves on it. So you have f of x, okay, which is the one that's more to the left. That is the parent function, which means that's the one you start with. And then, after a transformation, g of x is what you get over here. And so in this picture, this is showing a vertical stretch. The transformation is pulling the graph away from the x-axis. So, if you can imagine just stretching that curve, that's what's happening here. So it was closer to the x-axis originally, but now after the transformation, it's been stretched, so it's further away from the x-axis. You can also have a vertical compression, which is a transformation that pushes the graph towards the x-axis. So this is the opposite. So instead of stretching it and pulling it away, we're pressing it and pushing it towards the x-axis. So by multiplying the y value of each xy pair by a, where the absolute value of a is less than 1, the graph is compressed, in this case, by a factor of absolute value of a. So if a is greater than 1, it's stretching it. If a is less than 1, it's compressing it down. So in this case, the original parent function is y equals 1 and 5/10 to the x power. So this is our original one. It's a little bit darker in color. And then after I multiply everything by this value of a, in this case, this is an example to go with this, a is 3/10, and that's less than 1, okay? And so it does take our new graph, and now it's closer to the x-axis. It's pushed it down. So depending on if a is greater than 1, it would stretch the graph, or if a is less than 1, then it would compress the graph. And so again, you want to remember f of x equals a times b to the x power. This is the general exponential form of any exponential function, and exponential functions as well as linear, quadratic, polynomial functions. So so far we've learned about linear. We've done a lot of linear, and we're in exponential right now. We haven't got into quadratic or polynomial, but just so you know, they can all go under these same types of transformations. So whatever you start with, you call that the parent function. So that's what you start with. And then you do something to it to transform it. You can translate it. Okay, so there's two types of translations. And again, when I talk about types of transformations, so this may be something that was or was not covered in 8th grade, depending on where you were with the content you were learning. So in 8th grade, you do learn about some transformations. You learn about translations, okay, which are slides where you take a point or a shape that's in the coordinate plane and you can move it around, either left to right or up and down. And then that would be a translation. That's a slide. You also learn about reflections, where you have a line that you're reflecting an image over and it becomes like a mirror image. You flip it over the line. That's a reflection. Okay, so it's talking about these in this table right here. All right, so you have a vertical translation. So if you think about vertical, moves up and down, right? So if I'm sliding this graph, the parent function, f of x, if it moves up, well then what that equation would look like for the function you would have the original one, f of x, but then you'd be adding on some number here. And depending on if this number that you're adding is positive, greater than 0, that would be moving your graph up. If this number is less than 0, it'd be moving your graph down. And so I think what I'm going to do to kind of help you see what I'm talking about here, because it'll help if I open up Desmos. All right, so let's go ahead and just put in some random parent function, f of x, right? And so it's always a times b to the x power. So if I do a real basic one, like 1 times 1/2 to the x power. This is gonna, let me go back here. Let's not do that. Let's not do the half. Let's do the one that would show here where a is greater than 0 and b is also greater than 0. Okay. I guess I could do just 1. Try to keep it as like basic as possible. That did not work. Okay, I'm just going to copy this one for this example, just to show you how this is going to change, okay? And here we are. So I'm talking about a vertical translation where you add on a number, it moves it up or down. So if I come to this graph and say I add on 5, it just shifted it up. And, you know, what I could do actually is, let's make it so we have 2 copies. So there's the original one in red. And then I can show you. This next one. So if I add some amount to it, now it's shifted up. This blue one that just popped up is this new one because I'm adding a number, so it shifts it up. It's a vertical translation up. If I actually were to subtract 5 instead, it's going to shift down 5 units from the original red one. Okay, so see how it switched that time? So those are the translations ones. Depending on if you're adding or subtracting, it's going to shift it up or down. Okay, now here, the horizontal translation, f of x minus h. is a translation where if h is greater than 0, it's a positive number, you move to the right. If h is less than 0, it's negative, you move to the left. So I'm actually changing the exponent on this one. So I'm just going to rewrite this parent function. We'll call it the parent function when it's the original one you start with. And we had 3 times 2 to the power of x. Okay, but we want to change it so that we have either x minus something or x plus something. So if x is positive, then I would have x minus something, and that's going to move it to the right. So plus it's not letting me do that. I have to do parentheses. I do. Okay, so it works if I put parentheses around the exponent. So anytime you want to add in more than just one thing to your exponent, you're going to have to use parentheses. And so this green graph now, I'm going to turn off the blue one because I'm just comparing it to the original red one. I added 5. Okay, so it moved to the left because notice there's a subtraction sign here, so it's always the opposite. So this is like, I could actually do it this way too, so you can see minus negative 5. Okay, so there, I put in a value of h that is negative, okay, where x minus h, so I have x minus h and negative 5, and it moves to the left because this is for when x is less than 0. Now, if I want to see when it's greater than 0, I'd have to make this positive, and that's going to move it to the right. And that's what happened here. Our graph shifted over to the right. We have vertical stretches or compressions. So let's turn off this one. And I'm going to type in a new function, parent function again. We're starting with raising it to the power of x. Okay, but now I got to change this new one to do what I want to see here. So I want to show a vertical stretch or compression. And so we're talking about if I have a value of a being multiplied by x, then so if I change this 3 to a greater number, this should stretch it. We'll see what happens if I make it 10. It did stretch it, okay, because the red one was the original, and now it's stretched further away because I changed it to positive 10. If I make a number, that is a fraction, a proper fraction between 0 and 1. So maybe like 1/5. Now it's stretched, it's compressed it towards the x-axis. And the last one we're going to look at here is a horizontal stretch or compression. So horizontally, left to right. That's that way, stretching it or compressing it. What does that look like? So f of x, I'm writing the parent function again. There's the original parent function. This time it's in black. It's just overlapping the red one at this point. But now I'm going to change how b looks. So if b is greater than 1, it's a stretch. So if I make this number greater than 1, even more than it already is, like 15, what does that look like? Okay, so it compressed it towards the y-axis. If I make this number here, this b, a number between 0 and 1, so some sort of fraction, maybe like 1/4, that would work. It flipped it. So it does flip it when it's a fraction. But it is also compressing it. So I can make this fraction more closer to 0, so I can see it a little bit more intensely and change that to 10. And And so you can see the compression. It's moving more compressed towards the y-axis. I did this as 10. That's stretching it. So, like I said, I encourage you guys to play around with the Desmos graphing calculator. Okay, and so these pictures over here, these are just some other examples, like f of x is the parent function and g of x is the translation. So in this picture here, two things are happening. There is a vertical compression. So you can see in the original f of x, it has a y-intercept of +1. It's vertically compressed and reflected. All right, it got reflected over the x-axis, and it's now not down here at -1, which would be a true reflection. It's actually closer to the x-axis. It's crossing at a half, -1/2. And then over here, g of x is translated down by 3 units from f of x. So this is another example of a translation like I've been showing you over here, where you're starting with f of x, but then the translation to go down 3 units, that's a vertical translation. So that would be like whatever the function is -3. And so like right here, if I do this -3 and just turn this one on, same thing is happening. So that's a translation down by 3 units. Here's the original y-intercept, 0, 3, and it goes down 1, 2, 3 to 0, 0. Okay, so these different things that you might see in the equation of your exponential function will change how the graph looks. Use Desmos though, so you can definitely see what's happening, but these are these general rules that are going to show up. You're going to see that you would see that if you remember with linear, there's these same kind of things could happen. Not so like trying to compare it to linear. These same things would happen. Yeah. And then we'll see it, in future math classes as well. Quadratics, polynomial functions. Okay. So you guys are going to be on this last slide. And there's some different exercises. So 1 and 2, we're referring to these functions right here. And I want you to use the graphing calculator. Okay, so you need to open up a graphing calculator tab. Actually, let me just open it for you, because that's easier, right? I'll just force open a tab for you, for everyone. There's your graphing calculator coming at you. So you're going to use that. Let me take these out. And so you're going to actually type in these two functions here, first of all, so that way you can compare them and answer these two questions about it. So f sub 1 of x. You see how it has that little 1 right here, and there's a little 2 right here. You don't have to type that. The reason that's there is to differentiate that they're different. They're not both f of x, because they actually equal different things. So if you don't want to do a subscript, you could actually call one f of x and call the other one g of x. Or if you want to do the subscript, you can. Let me see where the subscript is. It might do it automatically. I'm not really sure. We're going to find out right now. So let me just type in as f of x and see. If I try to do another f of x, it might just throw in the subscript for me to differentiate them. If I try to do f of x again, now what is it going to do? E to the x power. It did not. It didn't differentiate them, but just pay attention to which one's which, okay? Or change the f to some other letter. You can do that. I know there's got to be a way to do a subscript, but I'm going to have to go watch like a... Okay, Tyler. Thanks for letting us know. Welcome. Yeah, so, when you do this, don't forget that with Desmos, when you first graph it, this is really difficult to see what's happening. So change your zoom. Zoom in and recenter it, and zoom in and recenter it. And then you can answer these questions. Question 1, which function grows faster as x increases towards infinity? Okay, so as x moves towards infinity, as we go to the right, as these x values increase, which graph is growing towards infinity faster? Which one's going to get to infinity first? The blue or the red? Which is getting the higher in the ordered pairs, those y coordinates, which ones are greater depending on the x coordinate? For any x coordinates, if I look at like right here when x is 1, you know, which one has the bigger y coordinate? Right here, the blue one. The blue one is this one. Okay, so then it says which one does that. Well, you got to tell me it's f sub 2 of x. If you want to handwrite it, I'd rather you just type it. Like what I would probably type is I would do f. I'm going to watch a YouTube video right now to see how to do a subscript on Desmos because I'm really curious. With this, you can't do a subscript, but you can go back and add it. So like if I just put a space there and then write 3 to the x power. Again, I can't do that exponent either, but I could go back and grab the pencil tool, and then I can come in and put a little 2 right here, and then put a x right here. All right, so you might have to get a little creative with how you write the answers. For the first question we did together, for the second question, it says which function approaches 0 faster as x decreases towards negative infinity. So you have to interpret this question the right way. So we want to know as x decreases towards negative infinity. We're talking about moving on the x-axis from the origin to the left. And it's asking you which one of these approaches 0 faster. Which one's getting towards 0 faster? Which one's always closer to 0? The blue one is always closer to 0. So the blue one is getting to 0 faster, approaching 0 faster. Won't actually ever get there, but it is approaching it. If you just want to type, I mean, there's different ways to write your answer. You don't have to write the whole thing, but you know, I need to put f sub 2 again. So I'm going to just use the pencil tool to go back and then put a little 2 here. If you don't want to write the part where it's like what it's equal to, saying which function it is, either f sub 1 or f sub 2 is fine. You could even write I'm just going to make this a little less complicated. Another thing you could write, so like another way of saying this, or you could actually write f sub 2. And I'll know what you mean because that means sub is like down here, sub level. There's a little 2. All right. That's not necessarily, this is not math notation. This is how you read this, f sub 2. So for Pear Deck, because it doesn't let you do math notation, you can do something like that. Okay, exercises 3 and 4. So what I did is I'm just going to toggle off 1 and 2. All right, and the ones I use for 1 and 2, and I'm going to look at these graphs for f sub 1 of x is 5/10 to the x power, and f sub 2 of x is 7/10 to the x power. There's my graph. I'm going to recenter it so I can see it. And it's asking me which function grows faster as x decreases towards negative infinity. So as x goes towards negative infinity, which one is growing faster? So as I move to the left, which of the 2, red or black, which one is going towards and growing quicker? Those of you that did try this. So this is correct. It's f of x. F, not g, but f sub 2 of x. It's the second one. This is a good idea too. Like this person is just trying to use like some way to identify them. Or, you know, because this is kind of hard, maybe you can like color code it. Color coding is great. So if I get a color coding here, if I make this one green and this one blue, okay, or maybe I should use the colors I have over there, but whatever. We figured out that the black one's getting up here first, which I'm calling that the green one. Okay, let me just use the same colors in the picture. I don't know why I want to make things more difficult. So the black one is this one. The red one is this one. And the black one's growing faster, so this one. I would type this out normally, but it's very difficult too. Yeah. And then says which function approaches 0 faster as x increases towards infinity. So now as we move to the right, which one's getting to 0 quicker? Which one's always closer to 0? The black one again, okay? So you do it that way, or you can just type it out. F sub 1. You could like label these with letters and then put like which one you want to. Okay, and then these last two questions. Label each of the following functions. G of x as a vertical stretch or a vertical compression of the parent function f of x. So if I look at g of x of f of x, I want to know, is this a vertical stretch or compression? And then the second part is to tell whether it is reflected about the x-axis. So here's where you're going to want to go back to this slide. This slide shows you if it's a compression or a stretch, if it's reflected. All right. And so a vertical compression or stretch, so vertical stretch or compression here, is a greater than 1 or is a fraction. So if I look at this, here is a, it's 0.7. So it's a fraction, even though it's a decimal. Maybe I'm phrasing that wrong. So the rule is a greater than 1 or is a less than 1 but bigger than 0? That would be a proper fraction, or 0.7 counts as what this would be. So this is a compression. That you can type out. That's nice because we can actually just type these words. Vertical compression. And then is there a reflection? Well, if you look back over here, a reflection, that depends. Is it negative? Is there a negative there or not a negative there? No negative. So no reflection. Okay, and if we look at number 6, I think we officially went over our time, huh? Yeah, class is officially done, but I'm still going to show you the last answer here, okay? Because what you're going to do is finish this and then take your 5-minute break, and then you're going to finish your paper math activity. So g of x as a vertical stretch or vertical compression. Vertical stretch, let's see, or compression. Vertical stretch or compression, is A bigger than 1 or is A between 0 and 1? A is negative 1 and 2/10. Well, if I don't include the negative and just look at the absolute value, it is bigger than 1, so that is a stretch. But then it's also a reflection because I have the negative there. Okay, so it is a reflection. It's a reflection. Okay, so this time is a vertical stretch and reflection. Another way to do these, okay, now I'm showing you how to do that by going back and referencing this table. You could also come over here and type these in to see what happens. Okay, you could type in both of these functions and see and look. Is there a compression from f of x to g of x? Is there a reflection from f of x to g of x? You would see these things happen. So you could visually look for it to happen, or you can use the rules that you have in this table here. 2 different ways, get the same answer. I really don't like how this is all inconsistent of ways of writing this. So I'm going to change my work just so it all reflects this more difficult way. You guys do what works for you. Okay, I'm not grading your pear deck. It's participation. It's there for you. You can use this, you know, to take your notes. Yeah, so I'm just going to change the way this all looks. But you're free to leave the meet if you are done copying. And I'll be on Go Guardian to help you if you need some assistance. Bye, guys.